Um, we want to welcome you to today's session, EORI Insights. I'm Lon Whitman, Director of the Enhanced Oil Recovery Institute, and we'd like to thank True Companies for hosting this event here at this nice facility. Cody, I think, is left, but he was here early, and we appreciate that. Today, we're going to focus on a Menalusa field in Wyoming, the Alpha field, where they've been doing some 3D seismic work to look at field development and how that can improve things at the field. We have two speakers, one live, Scott Ellingson with Zion. Scott's working with EORI as on contract on certain projects. And we're also really fortunate to have John Frederick, who will join via Zoom and talk about the 3D seismic. So we'd like to welcome everyone and thank you for coming here and online. We have a number of people also, so welcome. Scott Ellingson.
Thanks, Lon. All right, good morning, everybody. Thanks for coming and listening to me talk here for a little bit. Hopefully it's informative and something that maybe you can use going forward. But we're going to just talk about the exploitation and reservoir characterization of the Menalusa Sea here at Alpha. Exploitation is kind of what I've been doing my whole career, or for the last 14, 15 years. And so I figure, looking at a Menalusa, let's try and get some exploitation done here and find some more oil, because there's an awful lot of fields. Many of you are probably familiar with this. Stratigraphic column, Menalusa shown at the bottom, some muddy there in the middle. You can see some of the bigger fields here, Rosette, Timber Creek. As we move up to the northeast, Stewart is in red. Keeney Ranch is here in this area. And then Alpha Field is smack dab in the middle. I think Keel and Etzel are off to the east here. Just a few things that we'll be going over today. Menalusa deposition quickly, then the Alpha Field overview, the sequence stratigraphic approach that we took with this field, the seismic, and then conclusions. I just threw a little picture here of sand dunes and Sabka deposition here just to get us started. So here we're looking at this, some probably many of you have seen before. Here's the state of Wyoming at time of deposition. So this is late Pennsylvanian, early Permian time. You can see this shoreline going into eastern Wyoming, Powder River Basin. These yellow are going to be our aeolian deposits, and then shoreline sands in the orange, marine deposits out in the center of the seaway. And yeah, this was modified from this Heckel and Peterson, 1980. So this next one was modified from Gene George, Menalusa Consortium. If there's any flat earthers out here, this picture might be a little traumatic for you, but that's a chance I was willing to take. So this is modern day Qatar. As we zoom in here, you can see what kind of deposition was happening at the time, having these wind-blown sands being deposited into a shallow seaway. And feel free to ask any questions as I go. This next one is just kind of an image to get our heads wrapped around what we've got going on. So it's kind of a section that runs from A to A primed, and you can see it down below here. It's not working. There we go. So you can see it down here, up across to here, and what that's going to look like. You're going to have dolomites being deposited, hydrites and dolomites in between, and then your sand's going to remain. And we'll kind of come back to this in a second. So, we're talking about good rock here throughout this. You're going to have bad rock, real tight rock here, and then again, good rock, and you see that here. And so when I'm talking about good rock, I'm talking about porosity and permeability. So the background of this is from Freiberger down here, you can see. And what he was describing is your poro-perm relationship in dunes, then inner dunes and shore face. And, what we're going to be looking at here is inner dune rock, and then dune rock, again, inner dune rock. And so these red dots are actually plotted core data from the Alpha field. And you can see how nicely that they fit into this model that he provided. Now, this is a Weber sandstone, Sweetwater County, Wyoming. So it is a little bit different, but as far as deposition, aeolian sands, so it just fits nicely. And we'll talk about poro-perm relationship a little bit more later, but I wanted to touch on this while we were looking at this image of good rock, bad rock. You can see some numbers here. Average core perm 226. Millet RCs and porosity is 15.5. The slope of this line was used to generate my permeability logs that we'll use later. And you'll see those, but that's the slope of this red dashed line here. This slide is you're probably familiar with WGA papers that people would put out. The discovery well was this 43-2 well here. The James Lacey Federal 43-2. You can see its IP. This is a Minnaloosa B structure. Alpha field is Minnaloosa C. We didn't catch that earlier. Just real quickly, completion dates you can see here, 87 and 88. You know, most, I think, Minnaloosa fields were 60s and 70s, and so this was a little later in life field that was discovered. Once it was discovered here, they quickly drilled out and filled out the field. This was drilled in 1994. This is a number 2 well. We'll talk about that a little bit more in depth. This well was drilled in 91, and this was 86. So this was really the first well in the field. It was a dry hole, and then they came and drilled this well. But we'll talk about this number 2 well and this 13-1 well later. Here is kind of what we're going to be talking about is how can we exploit the areas outside of our injection response in this water flood. So here on the left, we've got a type log of the 43-2. As we run down, you can see this line right here is at 16% porosity. So you can see it's pretty much flatline porosity throughout this entire interval. Minnekata, Opeechee, etc. This is a computer-generated map just based on a isopac of over 65 microseconds per foot that's shaded in this yellow here. And so you start to look at, all right, I've got a 13-1 well here, and I've got a 23-1 well here. You know, how should I draw this? How can I draw this to best, just to best map it and also understand where the leftover oil could be? And so that's what we really want to find. We want to try and define this boundary of this reservoir and understand this reservoir as well as possible so that we can exploit it. Here's a graph of the entire field. So you can see most of those wells were drilled 87, 88. Nice big ramp up, started falling off, got unitized, and injections commenced. They also began polymer flooding this field almost immediately, I think immediately, when they started their injection. And as you can see, really nice response. The Alpha Unit 1 well was drilled here, just a few annotations. Public data has the production down here, but the field was producing in there about 1,500 barrels a day. And then the Alpha Unit 1 was drilled. It came on at 12 to 1,400 barrels a day for the first 9 months. So I kind of just drew a line in there. And then it started falling off. Not a lot to talk about here. The 44-2 was shut in. Polymer ceased. It came down. Not much to talk about. ESPs added. ESPs taken away. You can see it made 6 million barrels, produced 21, and injected 29 plus. So pretty good field. Not a lot of wells, and made 6 million barrels. So it's pretty good. Here off to the side, you can see we've got our oil per well, as well as injection per well. And on the bubble map, you can see down below, you got the well number, and then you've got our oil production per well. So the reds and hots are just going to be higher numbers. So 1.2 million, 1.7, 900,000, a million, and 465. You can see our injectors are here, and we'll talk about those more on the next slide. And then again, here's that number 2 well we'll talk about. It produced 85,000 barrels of oil. So not a great well, but a super important data point as we go forward. Again, just more background data on the field. Here's 8.9 million barrels injected, 5.7, 6.8, 7.3. So these are your big injectors here, and then our producers line up here. So you kind of get a feel for how the field was water flooded and what it looked like and what it does look like. So just a structure map with, now that we kind of understand the injection and production numbers. So again, your injector row, kind of injector row, and then your producers here with our structure here. Our highest structural point, I think, is 3295, and our oil water contact is at minus 3390 down here. Steep fall off on this edge, and it's pretty well defined based on this 2-1, number 2, and 23-1. So again, back to that computer generated map. Yeah, so this was pre-drill, pre-seismic. We're trying to figure out, we're trying to get this all dialed in and tightened up so that honestly, we want to move forward with the simulation. And we are with the EORI. And so this is the way the computer generated map looked beforehand. We're going to drill a well here. Oops, excuse me. We're going to drill a well here and shoot seismic. I wanted to point out that the original feasibility study done in this field in 1989 was 13.6 million barrels in place. In 1992, after they drilled this Alpha Unit 1 well, they revised it up to 16.6. And then we again revised it going forward. So it's kind of an interesting outcome of this. So to try and define these boundaries as well as we can, we'll look at this little cross section. You can see it's going from A to A prime. There's 4 wells. And so you can see the Minicata. This is a structural cross section with your B dolomite here, C sand here, and then anything over 65 microseconds per foot is shaded in yellow. From this, you can see 58 to 65 net feet of gross. Most of the wells are 1-to-1 net to gross. Top of the sand to base of the sand is all 1. Another interesting thing to point out is as we lose our C sand heading off the isopack in this direction, we lose that C sand and our B sand starts to compensate for that. So where we've got thin C, we got thick B. You can see that here. So that's kind of defining this boundary edge here. Here's that number 2 well, and you can see that there's 7 feet of sand here. Again, that well made 85,000 barrels. Now we're going down dip to up dip. You can see the sand is just really nice throughout. It's thick throughout. You get kind of a little bobble down here, but we're going from B to B primed in this direction and then off the sand up here. And so you can see what's going on. Your B dolomite just follows along as your C, like I mentioned before, pinches out, your B thickens up. And now we've just got one kind of going a long strike going across our isopack here, and you're going from C to C primed. So the 1112 is down here. You can see there's no sand there. There's a little bobble of sand kind of down here, but it's real tight. And then as you move over onto the 4111, you do pick up, there is some B sand here, but it quickly goes away as you get back into the major part of the field. C sand coming across. Yes, sir. The B sand is perforated as a disposal in this wellbore. These perforations were added in 2021 maybe, and I think it's putting away 80 barrels of water a day is all. Yep. So these are the same cross sections, but this is where I want to go from raster images to LAS. I tend to go back and forth between using them both. Raster images have some detail that you can't see in LAS. And so that's what we're going to look at here. And so we've got the same cross section in LAS, and it's a lot of colors to look at when you first look at it. But if we just take a second, we're going to talk through this. So this black line is gamma ray here off to the side. And then in the same track is our K. It says KH, but it's our permeability log. And it's in this red here running down. And you can see it going here and color shaded. And then we've got sonic porosity in this column here. What we got shaded here in orange is anything over 15%, and then yellow is basically 10 to 15%. So you can see what the sonic porosity is here. Almost this entire log is well over 15% porosity, and really it's approaching over 20%. And some of this is getting up into the 25% porosity range. And so what I use this for is to apply that transform from the poro perm curve that we looked at earlier to generate these permeability curves. So what I'd like to point out is, like in this 4111, you've got a few streaks of 15% porosity throughout it, but overall your permeability is pretty low. We're looking at, I'm sorry, I didn't say that, but 0 to 200 millidarcies. So this, for example, is probably sub 50 millidarcies for this entire wellbore. Whereas you move to the 44.2, and you can see much of this is over 100 millidarcies, and there's places in here that are over 200 millidarcies. Again, tight, low perm, lower perm, and then off the sand. So you can see there's something going on here that I think is more, we need to look into more. And so that's what we did with the sequence stratigraphic approach. This is just one more that's a little bit cleaner looking. We're going from D to D primed, and I don't think I have it marked on my map there. But the 2-1 is going to be this well here, and then it's going to head to the south here like this. And so, what I'm trying to show here is that you go from the 2-1, that was a 1 million barrel well, and you can look at that K, the permeability log through there, and it's tight throughout. You move to the 13-1R, and we've got over 150 millidarcies, pretty much the entire section. And then you get back to 13-1, and you got this tight, good perm streak here, good perm streak here, tight again, good perm streaks, tight again. So we're starting to see this, and you might be able to start to pick out with your eyes, like, good, really good sand, pretty good sand, really good sand, really good sand, really good sand. So is there something going on there? So this is kind of just a schematic. This is adapted from Freiberger, just to show that you've kind of got these low perm rocks on these edges, and then you've got these really high perm areas. So if we take this 44.2, there's going to be a really high perm area around this wellbore, and then you look at these kind of high streaks in here, and those are kind of how they may look in a cartoon sense. It's not drawn with, this is just a qualitative look at this so that we kind of can wrap our heads around it. If I was going to explain it to my kids, this would help them look at it. And so if I explain it to them, I can explain it to myself. So we talked about the Malibu Fed 2-1. You can see the overall permeability in this well versus the 13-1, and that's this other well here. We'll talk about that. And the 13-1 is right here. And you can see it's got one nice 200 millidarcy almost streak in it, and some more porosity down at the base. But the average permeability for these two wells is quite different. And so when we look at this is the 2-1 well way up to the northeast, 6 years of flat production at 300 barrels a day. This well, the 13-1, was 800 barrels a day. And I'm talking about response after water flood. And the big thing to take away from this is the deliverability. The deliverability, I think, is going to be the key in being able to exploit this Menalusa Sea to its full extent. And so you look at this well, and you got to figure in a few things. Pumping unit's probably going to move at these depths 300 to 400 barrels of fluid a day. Anything more than that, and you're going to need an ESP downhole. And so this well, if you look here, was 1,000 barrels of fluid a day types rates, over 1,000 barrels of fluid a rate. Whereas this 2-1 was 300 barrels of fluid per day max. And so the deliverability in these logs is what's key here, and kind of what we'll be focusing on for our exploitation. Now we're going to take this into sequence stratigraphy. We've kind of defined or tried to define our boundaries better of the reservoir itself. Now we're going to try and look internally so that when we simulate this, we have the best chance of getting a correct history match. So this was taken from a Freiberger, Jones and Johnson 2014 EORI paper. This is the Ranch A historic place just outside of Beulah, Wyoming. It's a really pretty canyon to drive up sometime, but we're looking at Minnelusa outcrop here. Each one of these lines are separated by probably 8 to 15 feet, but you can see there's parallel bedding along all of these, or sub-parallel bedding along these. So this is kind of the idea, the approach from a outcrop perspective on how to do this sequence stratigraphy. And so now we're going to take that into the raster log world. The exact process of using sequence stratigraphy here, I'll let Stephen Whitaker go through. He's got some information out on it that he would, I'm sure, gladly sit down with you and go through exactly how this process goes. It's not super complicated, but it takes a while because there's a lot of picks. But basically what we're looking at is finding a level flat spot, either above it or below it, that the sand was being deposited parallel or sub-parallel to that. So in this case, we used dolomite below us to try and pick, and then we're picking tight streaks in between. And this is one of the better logs that you can see some of those tight streaks. So you got real good, nice porosity coming down, tight streak, nice porosity, tight streak, nice porosity, tight streak. And so those are falling in line with these. And same with if you look at the porosity, the core data. If you look at the core data, it's interesting because you'll look at the porosity and see like 15, 18, 17, 16, and then all of a sudden you'll see like 1%. And then same thing back. And you'll see this like every 8 feet. And the more core data you look at, especially with this Minnelusa, is that break every 8 feet, every 6 feet, every 10 feet, where you got this one little tight streak. And so that seems like what we're seeing here. And so we're trying to define that by using sequence stratigraphy to help us. So I've just labeled C1, 2, 3, 4, 5 here. And now we'll kind of go through each one of these and what they look like. What I've done is taken the permeability log and generated a KH for it. So I took this log and just like a pH, I used K and generated KH logs. So here we've got, for this first slide, I've got the API series number down below. Modelers and simulators use the 5-digit API. I think engineers do, where geologists use the well number. But so I put that on this slide. Then it's the well number above and then the data here. So for this particular well, you can see that we've got 5,300 feet millidarcies over this. So if it's 10 feet, we've got an average of what, 530 millidarcies. So really porous rock. And you're going to see that in this 44-2 well throughout. And at the end, I'll kind of summarize with some seismic of why that could possibly be happening and what's going on here. So for this very upper layer, this C1, you can see this is really the only well that's got much. You can see there's an 800, a 700, but zeros out here, single digit kind of numbers. And then we'll just work our way down through this and you'll start to see. So here's C2. now we've got something else kind of forming. Now we've got kind of a dune shape forming with this little saddle in between. As we scroll down, all of these are on the same scale. So when we get to this slide, this isn't a figment of your imagination. This third zone in this field is just absolutely gorgeous as far as porosity and permeability goes. So you can see a 7,000 number here, a 9,000 number here. The rest of these are 2,000. So, you know, this is how you're going to pass water through from well to well, even though you've got no sand in this upper interval in these wells, it's going to be able to get out here through this zone here. Again, we drop back into like a lower perm regime. And this is the first time that this isn't the highest perm, the highest KH in the field. This well is kind of taken over. And this is the 13-1R, and that's the well that was drilled after this has all kind of been taken in. And then the last one is the C5. You can see these are the only two wells that really have much of it. The 13-1's got a little bit. So that kind of, you know, brings us to a point where we've kind of done our best to map the boundaries of this reservoir. We've looked at the internal stratigraphy of this reservoir. And so now what's the next step? What tools can we use? And so we got a hold of John Frederick and decided to shoot a 3D seismic. And so I'll let John take it from here. And John, are you there?
Great. Yes. Good morning. Can you hear me? Yep, I'm here. So Scott, can you let me know if you can hear me?
I can see him.
Yeah. So
You have a question, Srishan?
just want to know if you could hear me. In terms of the video, can you hear me?
That like a part going very steep, fastly, and but that one is very slowly.
I mean, I think part of it is because your permeability is so much lower overall. This well is to the north and east. And this 13-1 is more of a direct offset to this 43-2 injector. And so, you know, as this 13-1 is taking that much fluid, you're just not pushing water directly between those 2 points. Because it's going this way, this is only seeing pressure and maybe not that big water flood front and fast breakthrough that this saw. Yep, this is it. It was. No. So this does not. It was pumped off. This well is pumped off at 300 to 400 barrels of fluid a day, and so that I should have mentioned that earlier, and I apologize, but. This is a pumped off rate where this is, 1,400 barrels of fluid a day and 2,000 feet of fluid over your pump, probably. So, I mean, this well could probably make 2,000 barrels of fluid a day. Right. Yep. Trying to get John on here. John?
So Scott, yep, I'm speaking now. Can you, any audio coming through? Can you hear me at all? Okay, well, yeah, Scott, why don't you go ahead and explain those seismic slides?
Yeah.
Oh,
Oh, there's stop share. Go. So there he is.
Yep.
Let's see.
sorry for this, people. We'll get.
We want to share your screen. Stop share. Try that, but I think it's gonna. What we need to do is allow John to share his screen.
Well, he's going to use mine.
Oh, he's gonna use
His
yours.
microphone's
Right.
just not.
Okay.
Yep. So the microphone's not working.
Yeah, I think
Okay.
it's on.
See the volume right there.
Yeah. I don't know. Hey, John,
Yes.
can you
hear
can
me?
hear us, but we can't hear you.
Right. So why don't you go ahead? You explain it. Go
Can
ahead.
you hear it on yours? You want to turn yours up and or should see?
Stings. There we go.
Can
Hear you.
you can't hear John?
No.
So we can, okay, so I'm speaking
There's
now.
John.
There you go. Does that work? All right. All right, Scott, can you hear me now? Everybody hear the voice? Okay, great. Thanks. Well, good morning to everybody. So yes, as Scott said, why acquire a seismic survey over this field? I mean, it was a field that had produced for a long time. Two questions came up, actually three, but one, the first one was, are there any additional locations? Even though that is a closely drilled field on 40-acre spacing, are there any other locations? And so that was one way of using the 3D to see if there were any additional locations. And then the other is, can we improve the characterization of the sea sand dune complex for the recovery process? So will the seismic give us even a better idea, in addition to the subsurface data that we have, of describing that field, maybe understanding why certain wells perform and have a better response to the water flood than others? So those were the sort of the two key drivers on the 3D seismic survey. So Scott, can you advance that slide? Thank you. So this picture of the topography of Alpha Field, you can see where the existing well locations are. It's just, northeast of Gillette by about 10, 15 miles or so. The terrain, we did have some ravines in there and some hills, but it was pretty simple. And so we were able to put a 3D seismic survey in this area without much of a problem at all. And this was the source we used here. As we go to the next slide, Scott can flip over to the layout, was Dynamite Survey. And it's been my experience in the Powder River Basin over the last 40 years or so that Dynamite data gives you a better seismic response in terms of frequency content. And the frequency of the seismic data is key to being able to start to get better resolution. I'm not going to say we can resolve sands totally, but you get much better resolution on being able to tie in thickness of sands with the well control. So this map on the right-hand side here, where you see the triangles and the dots, the triangles were the shot points, and the dots are the receivers. And so we had, the layout was, it was, as most of the seismic surveys, 3D surveys now are acquired, high density in terms of receivers. So you can see on this survey, which was less than 2 square miles, we had over 2,000 receivers. And that is a picture that Scott has on there of the node. So that's recording at one station. So they were 110 feet apart in the east-west direction and 220 feet apart, the receiver lines in the north-south direction. So that it was a high effort, probably about 200-fold. So compare that to 3Ds that were shot in the early 90s that might have only been 12-fold. You mean 12 traces per subsurface point. Now we're up to 200. And that just helps with the signal to noise and the resolution of the data ultimately. So we can go to the next slide there, Scott. All right, so field work. The track drill. So the left picture is a track drill. It's an auger drill. We drilled holes about 70 feet deep, loaded them with 16.5 pounds of dynamite. And you can see there it is. There's the yellow tube. There is the dynamite string that then we attach caps to the drillers and load it down the hole at 70 feet. And the far right picture is actually when we were recording the data. That is one of the fellows hooking up the firing line to the caps that are on top of the dynamite, getting ready to shoot that source or to detonate that source, which then gives us that sound wave that we record with all those 2,000 plus receivers. Next slide, Scott. So one of the things we did first was when we processed the seismic data, and these are 2 traverses that you're seeing there, 2 east-west traverses, both on sort of the middle to northern portion of the survey. In order for us to really understand what the seismic response is that correlated to in terms of where the sea sand is, where the minicata is above it, and where even the Cretaceous zones are, we then took and made synthetic seismograms. So we just take the well log, and Scott is pointing to the middle one there. That well log and the one to the right, we were fortunate enough that the when those wells were drilled, they logged from above the Cretaceous, or right about the Cretaceous, from the Dakota, muddy Dakota, all the way down to the base of the log. So within those red boxes that you see there, those are synthetic traces. That is not the original seismic data, but those are seismic traces generated from the well logs themselves. And you can see how consistent the seismic data matched the well logs. That gave us a great deal of confidence that when we started interpreting the changes in seismic response toward the bottom of the slide, where Scott has his cursor going now, that those amplitudes and so the troughs and the peaks, where they were positioned in time, and also their amplitude, we can then interpret the seismic data using the well logs there. So we had a very, very good correlation with the well logs. And on the right-hand side, the right slide, you can see where we have a thick sea sand. That is that strong response. It's the trough. So it is the peak, which is colored in black, is what's above it. And then as we moved off to the right on that well to the number 2, the trough position changes and the peak changes. And we'll show that on another slide, but that shows the edge of that dune complex. So we can go to the next slide, Scott. Okay, here we've zoomed in on the seismic interval that we showed in the previous slide. The yellow line on the maps above it is the position of that seismic traverse. The map on the left-hand side is Scott's map. It is his ISOPAC from basically the top of the Opeechee to the top of the Menalusa sand. And when we have a thick sand, when we have a thick sea sand, then the distance between the top of that sand going up to the top of the Opeechee is going to be thin, right? So if you think of it as you're have this a bottom layer, which would be the sea dolomite, and you're going to stack a very thick sea sand, then what is on top of that is you get a thinner Opeechee and whatever intervening dolomite is on there. So the purple is on Scott's map is the thin isopack, which represents the thick portion of the sea sand. Okay. The corresponding geophysical map generated from the seismic data, the 3D seismic data, is measuring from the peak, the Minnetonka, which is basically the top of the Opeechee, and to the peak above the sea sand, which is essentially the top of the sea sand. So that the greens and sort of light blues are the thin isochron, meaning the time is thin. So that is where the sea sand is the thickest. And then as you roll off and you see the grays and the purples, those are thicker isochrons, meaning there's more time there. And so that shows where the sea sand is thinning. And if we just looked at the seismic traverse below, you can see where I've highlighted the sea sand interval. It is in yellow. You'll see that in the isopack values of the sea sand are in red above. And so if we go from left to right, you see where we have a thick sea sand interval at 58 feet. The next well is at 62. And so if you're looking at that sea sand, you'll see that above the yellow highlight there, we actually lose some of the amplitude on the peak. And as we lose that, that peak is generated by the base of the Opeechee and whatever dolomite is above that. And so when that's another interpretive technique we're using there. When we see that very low amplitude peak that sits above the sea sand, that corresponds to generally a thinner capping dolomite. And we get that thinner capping dolomite when we have a thick sea sand built up. So we can, this corresponded very well to the existing well control. And then as you see, as we go off to the right to the 23-1, where we have basically no sea sand porosity, you see that there's a seismic waveform change there. We get a very strong peak above it. And actually you see that peak sort of drooping down. And so that, this picture that we have here, you can envision that that is basically the sea sand dune. And then as we go off to the right, it's thinned. And so think of Scott's picture when he showed you those dunes in the very beginning of the presentation, that so in that sea sand interval, we have a thick dune and then we're falling off the face of the dune. So there we go. So here's, that's a great slide there, Scott. And so this traverse is going up. It's basically in the dip direction of structure, but it is traversing sort of the longitudinal part of the sea sand. And again, you can see the thick sea sand buildup. And then as we get to the number 2, which is a producing well, but it has thinner sand, we start to drop off. And you see that seismic waveform change. You see that very strong peak in black that Scott is pointing out right there. And that is where the sea sand, where the edge of that sea sand is. And it shows that on the map. It's about where his star is, or on the depositional edge. So we were able to use the seismic data, the 3D data, to basically, not basically, but it ended up confirming where the biggest part of the sand dune complex of that sea sand is. And then it also showed where the edges were. And so that was good. And I'll just add a point here that Scott has probably taken into account or will. Just looking at that seismic line that you see it below there. If you look at that again, peak above the yellow, above so that's basically the capping dolomite. An interpretive tool would be is where we see that peak becoming very weak, we probably have a thicker sand. And then as we see it getting stronger, we still may have a thick sand, but it probably is a bit thinner. So that can be used in trying to understand the actual topography on top of that sea sand complex, because it's not just a perfect, flat surface in dip, but you have obviously some topography on top of those, the sea sand dune complex in there. So we can use that interpretive tool as well. So that is the key parts of the seismic data. And then Scott, I'm going to turn it back to you. You can then go ahead and show how the seismic data then integrated with your subsurface modified your original subsurface map.
I got a quick question about John, this is the answer there. When you see that B, you have that, Scott, you have that B map. Is that a complicating bigger B model that you're describing here? Does that dim out that upper dolomite?
Does the B sand, so yeah, just here, so you're asking, does a thicker B sand dim out the dolomite? The peak above? Well, typically, yeah, that's a good, excellent question. The answer is no. Actually, even that, as you get a thicker soft sand, in this particular case, above it, so you have a B sand on top of the B dolomite, the impedance change, the dramatic seismic change ends up, you get actually a stronger peak. So if you have again, each case is different, but in this particular case, as you see where the number 2 well is, as you get to a thicker B sand on top of the C, that peak between the two, between the trough that represents the B and the trough that represents the C, actually has a higher amplitude. So that shows that you probably have thinner C, and that brightness that we see right there most likely represents a more porous B sand sitting right above on the B dolomite.
Okay. What's your usable frequency here?
The frequencies of this data that we had, I think this slide is probably 90 hertz, but we actually had higher frequencies than that. And that is, as I mentioned again, the key on dynamite versus vibrosize. My experience with vibrosize is that there's sort of this natural earth filter in the Powder River Basin, at least in the Minnelusa portion. So we're talking about, two or three townships south of Gillette, all the way up to Montana border. The vibrosize data, no matter what frequencies you put in the ground, you can sweep up to 110, 120. You can do nonlinear sweep. You can do whatever you can to increase the frequency content from with vibrosize. But there's a sort of natural earth filter, and essentially it stops at about 70 or 80 hertz.
Okay. John, thank you very much.
You are welcome.
So we talked about the computer generated pre-seismic and pre-drill map. As we worked through it, we defined some of these boundaries better, predominantly using the seismic. So as John talked about and pointed out, and I'll reiterate here, this number 2 well is on our boundary. So that's the well we saw 7 feet of sand in. If we go back and look at cross section here, here we go. So this well right here, you can see very thin compared to any other wells. And so when we were defining our boundary with our seismic, this was a very critical well, and it helps us determine, okay, we're good out here to 85,000 barrels. So that means, can we be good out here along this edge to 85,000 barrels? And can we do better than that? And how can we do better than that? So big changes from this map. Our boundary is well defined, and that's just straight out of the seismic data. And then our ISOPAC pulled out. A lot of this was showing that our thickness throughout. So we could be a little bit more, I think, realistic when we're drawing these contour lines coming out. You don't really know what you're going to see between wells here, but with the seismic data, it felt pretty confident that we could say that we've got this in our isochron. So maybe we should be able to see at least this in our isopac. So that pulled these contours out, as you can see. Drilling this well also pulled the contours out, but steep boundaries on this. I think some of you may know better than I do, but you know, the boundaries on, I think, a Minnelusa reservoir may not be this steep in some fields, especially B reservoir, but the C sand for this particular field seems like it has very, very fast runoff, because we got 40 feet in the 2-1 and we got 7 feet in the number 2. And so we've got pretty good well control. Kind of just to wrap things up, we talked about 6 million in place and injection volumes. After doing this, I'll point out this structure isopac maps on top of each other so that you can see kind of what's going on full field. With this study, we've now bumped up to 19 million in place, which is, I don't know, does it really matter? Yeah, but does it really matter? Probably not. You want to go drill a well, and what are you going to get from that well? It doesn't really matter what the in place number is necessarily, but so from this, we were able to firm up 2 PUD locations on this eastern edge. And I think the key to those is, like we talked about before, is that deliverability. This number 2 well, that made 85,000 barrels. I've said that, I think, 15 times now, but it's 50 barrels a day flat for what, 2.5, 3 years, and then it falls off. But again, back to the deliverability, you're seeing max rates of 30 barrels of fluid a day, you know, so that's pumped off, and that's all that rock would give up. And so as we look throughout the field, how can we kind of figure that out so that we can make a well that makes more than 30 barrels of fluid a day, but doesn't make 1,500 barrels a day? And so with this, we're able to look at, all right, if I drill a 20-foot sand out here, what's my deliverability going to be? If I drill a 30-foot sand, because with the deliverability is when you're going to see water breakthrough quickly. But if you can go drill a well that's got double this deliverability, you're going to be talking about 100 barrels of oil per day flat for some period of time before it breaks over. And that deliverability, like I was saying, you know, if you can get 300 to 400 barrels of fluid a day and start off with a pretty decent cut where you've got bypassed oil on this outer rim, I think that you can make some good wells. Now, these aren't the 1 million barrel exploration wells, but this is exploitation. So 2 ways I got to 170,000 barrels. One was volumetrically. There's about an 8 to 10 acre area in here, both outside near this number 112 location and 114 location. In those 10 acres, I think the in-place number was 510,000 barrels or something like that. And then I used a 30% recovery factor to give us 170,000. Now, these 2 wells, when I did volumetrics for this area, the recovery factors for these 2 particular wells were 40%, over 40%. If I applied that to these 2 drill wells, you know, being in the less perm, you know, less porosity area on the outside, like these 2 wells are, if I applied that 40%, we're going to be around 200,000 barrels each for those wells. Then you let the finance guys figure out the economics, but I think those are real reserves. The other thing that we avoided that I hadn't pointed out is that even from the old feasibility studies, they usually had a big nose coming up this way. And from the seismic, there was a drill well out here from the feasibility study back in 1989. It looked like a good location. It looked like, you know, if you map this sand coming, it's going to do this kind of thing out here. But we were able to avoid a dry hole. There's plans for drilling these wells, and there's plans to drill more possibly, but along this edge, we avoided drilling a dry hole because we were going to be drilling somewhere in here where we've got dry hole out here, got a dry hole out here. kind of split the difference and maybe move it in a little bit closer. So we avoided that at 800,000, and for all the seismic and the interpretation, all in was 266,000. So if we've generated 300,000 or under $1 a barrel for a finding fee for this, and we saved a bunch of money on dry hole, possibly. So our next step is going to take this, now that we've got a pretty firm geologic model constructed, we're going to take this and put it into a simulation model that Shritron is doing, and we're actually doing that. He's doing that right now, hoping to see what we have for oil saturations that are remaining. This is just from an unfinished product for this field that Shritron is working on, but just to kind of tease you a little bit, maybe more than anything, or myself, but initial saturation remaining, here's going to be our drill well, straight south of that well, straight east of this well right here. And you're looking at 70-80% oil saturation, maybe higher. So that's what we'll be looking for, to possibly drill a well and get this firmed up and see what we can do out here. But that's it for today, I think. John. Yeah, this 11-12 well right there, 1986. I'm not entirely here. And then out from there, you had, I think, this well and this well. And you had another B sand dry hole up here. So I don't know if they just saw this hole in here. I'm not exactly sure why they kept, or they drilled, but I mean, it wasn't a unit at this time in 1986. But they had this data point and that data point to try and get their way in between, I think. But no, there was a little bit of sand. Let's see that one. This well right here. You can just see that it's just this little C blip is trying to show up. I think you got 6% in there. But that's what they would have been looking at coming from that well and trying to go northwest. But when you look at the seismic and where they ended up drilling these wells, they had the reservoir defined quite well out here, which makes me wonder if they had some lines going across or a 3D that I couldn't find. And I'm glad we shot 3D, a dynamite 3D, because this data is incredible. I mean, it looks beautiful. And to be able to tie it in with the synthetics the way we did, and working with John, it's been fun. But yeah. Another question. Yeah, so 60 feet. I don't have a good, but this is 60, so the Upichi is 60 to 80, probably, depending on where your top or base of your Upichi is. It's a really interesting field, and you're good. Mm-hmm. So
Is that-
I-
is that- it's carrying so somewhere that stamp starts changing.
you're talking about over here? Mm-hmm. Mm-hmm.
And then some B sand. Yeah.
Yeah. So there really is very little B sand where we have any C sand over the field. So this, I think this is B out here. John is definitely going to be your better answer on this, but I think this is B sand that you're looking at out here, how you get this peak and trough, a new peak and trough, I guess, up here. Because we know from logs that as we head this direction, our C thins hard, and then our B thicks up. And there's actually a big B sand that sits kind of arcuate in here like this, that's 40, 50 feet thick. And so I think that's kind of what you're seeing there. Mm-hmm. Oh, okay.
I'm worried about is up on the northern area up there. Maybe some. When the two producers were those two right there. Yeah, that up in there, there may be some. Some potential target up there. Have you thought about that one up there?
Yep, we've kicked around, and we're still, Treetron's not done with this part yet. So we gotta work on this a little bit more. But yeah, I think there's definitely could be some locations when you're looking at this that are going to be structurally high. Oil water contacts minus 3390. So you've got plenty of structure up here. Right. Something. Yeah. 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 So I think that's it, unless there's any more questions. That it?
Thank you, guys.
Thank you guys very much. Oh yeah. Thanks to Lon Whitman, EORI, and especially John Frederick. He's awesome to work with. Shameless plug for him, but he's great. So if you can work with him, but that's it. Thank you guys.